30th of May, sorry.
Yeah, I'm planning to go. I haven't looked at flights yet, but I'm planning to be there the whole Monday. Yes, flying on Sunday and come back on Tuesday.
Okay.
But yeah, I haven't taken care of flights yet.
Okay. So maybe we wait a couple of minutes more.
Sure.
Apparently, YouTube has blocked your lecture.
Really? What?
Now, we have the streaming. The streaming is stored automatically on YouTube, but now Maxime, our technician, is video edited. I prepared a video edited copy, and he uploaded it and was blocked by YouTube. We don't know. So we discovered this today, and we will write for, I don't know, maybe Resurgence is forbidden. I don't know. Or maybe it's the first time which happens.
All right.
I don't, just formulas. I don't know what bothers YouTube. I don't know. Maybe there are your. No, you have it on the top. I cannot say the word, but behind you on the top of your library, you have some cans, and we see the brand. I don't know.
When I was
maybe they fear some advertisement. I know. I'm joking. I don't know. I really don't know.
Well, it's the most popular brand.
So okay. So okay, I guess that so we passed the wall of 10 persons, so we can start, okay. I guess. And so thank you, and you may go.
Okay, and, thank you very much. All right, so what have we done in the past two lectures? Basically look at the simplest possible example I could come up with. So I think by now, everybody should have sort of some good grasp, good ideas of what Resurgence is, how it works, what are the main players, and so on. So what I wanted to do today is to formalize a couple of things. Let's see, I just realized that I'm actually late on the global structure of lectures, but we'll see. So I wanted to formalize a couple of things, just so that the language is, I mean, I won't be ultra rigorous by no means, but slightly more rigorous than what we've been doing so far. And then that was my goal for the first sort of hour. And then in the second hour, I started already going into applications and saying, why do we really care about all this? I mean, up to this moment, you could say, well, this is some very interesting technicalities, but why would I care when I do day-to-day theoretical physics, string theory, whatever? So I want to motivate that a bit. It's unclear if I will manage to do both things, but at least I hope to formalize a couple of things a bit more, and then we'll see. Anyway, so for the last lecture, I'll be in Paris, and then worst case scenario, I will do a slides lecture if you guys don't mind, so that we can cover all types of applications instead of a blackboard. Okay, so without further ado, let me start sharing the iPad. I think we can go straight there. Okay, here we go. Okay, so again, all we're going to do today is formalize a bunch of notions. So the first half an hour is just giving a little bit more rigorous names to all the things we saw in these examples. Okay, so let's go step by step. So the first thing I should warn you, it's not a very big big warning, is that what we've been doing up to now was perturbation theory around x equals 0. I'll now be doing perturbation theory around z equals plus infinity. I mean, this is just a minor detail, just because in the math literature, formulae are usually written in these conventions. So just to make the parallel. I mean, part of the goal of also what I'm doing now is that when you want to read, purely mathematical works on Resurgence, and by the way, there's 2 excellent reviews by David Sauzin, very, very formal, that if you really feel like you have the courage to go into them, I strongly recommend. So just to make the parallel with that notation. Also, by the way, when we're looking at matrix models, this is very much the case that we're doing, large N expansion. So this is also the standard sort of formula that you should see appearing. So if we start doing perturbation theory around here, so now I will be writing my perturbative series in this way. By now, it's something which is highly familiar. So really nothing very weird going on here. And of course, what I'm expecting is for these guys to grow factorially fast, but now it can be slightly more precise. So I'm expecting that what's in green should happen, but I can be more precise because there's different types of growths. I mean, there was a question in one of the early lectures about that. And so we're going to define a Gevrey P series. If it's asymptotic in the following way, there are positive numbers such that the coefficients grow. There's a bound, there's an exponential growth, and there's a factorial growth to the P. And in fact, let me change the color of that guy. So that's the Gevrey P series. So you see that now we can allow for more general types of growth. And the growth we're interested in all the time is Gevrey 1. And in fact, all the examples we've worked with so far are Gevrey 1. This is not to say that there won't be examples out there which are Gevrey 2 or 3 or whatever it is, just so we can talk a little bit about it. So if we're dealing with these more generic, by the way, Gevrey 0 would be a convergent series. That's also included. That we never care about. That's why we're sort of in the first order of difficulty when we're doing Gevrey 1. So what would we do then? Just so very quickly, there's some, you can generalize the Borel transform to have an index. So this would be the, maybe I should write it first. Index Borel transform. And then I just write it like that. There's the M. Now I'm just, the perturbative guys are now 1 over Z, right? And I just define it this normal way. I'm not gonna, this is, so there's a whole story of multi-subability here that I'm not gonna very much get into. Let me just put the M's in a way that you can see. There's where they go. And then we can also, do the usual game, do the Borel transform, do the analytic continuation, and eventually, once I do the Borel transform, I will find a non-zero radius convergence. I can do analytic continuation, and so on, and then I can define the index. In this case, it's going to be 1 over P. That's because of the Gevrey P growth. So when I'm dealing with Gevrey P growth, I define the index 1 over P resummation. And I'm not going to dwell anymore into this because, it should be sort of everything that I've been discussing just basically holds. I'm just going to put around in the zeros direction. Here we go. It's a slightly bigger formula than usual, but anyways, so that's a Laplace type integral that can also be. So there's a whole story of multi-summability. Just put the P's there. There's a P 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 there. So you can play a little bit. So type of exercises that students can do is just play a little bit with this formula and reproduce similar formulae to the ones we've discussed earlier in the lectures with this sort of index M Laplace transforms, try to deduce properties of these index M Laplace transforms and so on and so forth. Okay, so as I just said, so our interest is Gevrey 1. So from now on, let's focus on Gevrey 1, which is what we've been discussing in these ultra simple examples I gave earlier. So let's focus on Gevrey 1. And let's say a couple of things about Gevrey 1. The first thing is, what is a resurgent function? So that was sort of motivated. Well, I can give you the slightly more. This is, of course, due to Ekal in the 80s. And the one-word definition is resurgent function. Resurgent function is basically an object whose Borel transform has endless analytic continuation. So there are basically no natural boundaries on the Borel plane. Okay, so you can see this is an ultra broad thing, and in fact, all I'm doing in this lecture is just scratch the surface of all this resurgent function story that was developed by Ekal. I mean, basically, there's you know, almost anything can be. Of course, there's examples. You can cook up examples of things which are not resurgent just by having natural boundaries on the Borel plane. But I mean, we'll assume that. Well, it's not even an assumption. In every example that we've said so far, that didn't happen. And in fact, something slightly better happens is that in all examples we've seen so far, more than resurgent functions, we've been dealing with simple resurgent functions. And simple resurgent functions, basically, again, a one-line, one-sentence definition is a resurgent function whose singularities restrict to basically what we've been looking so far. Simple poles, which I will not put in, they're always easy to put, and logarithmic branch cuts. So here's the Borel residue at singularity around omega times the Borel of another sector times a log branch cut. And as usual, I'm just writing the discontinuity. So of course, there's a bunch of holomorphic stuff that I'm just putting under the rug. So let me put there dot, dot, dot. That's all holomorphic that I don't care about. So basically, the simple resurgent function is something which has a log and a pole. The pole is associated with the residual coefficient that we discussed earlier. Not so concerned about that. So it's basically a log branch cut. So omega here is the simple, I use the same name, singularity. S omega, of course, is just a complex number. It's the Borel residue. And psi is some other sector, which is resurging at this singularity. All right, so again, there's not a whole lot more to say. And once I do a simple resurgent function, I immediately grab the formulae that we earlier discussed for discontinuities and for Stokes automorphisms. So I mean, now this is almost straightforward to obtain because I write now here is something we've already seen. I just write the lateral Borel resummations, which I'm writing for the, oops, that's a theta, which I'm writing for the infinite time. Just to write Z. Yes?
This simple resurgent function, you mean it cannot have pole, could it?
No, that I just said that. So I'm never writing the pole. So whenever I write a log, there's also a pole associated.
Okay, I see.
But because it's always there, so that I just write slightly faster, I'm always leaving the pole understood. I mean, we wrote the formula with the poles in the first slide that you can review if you look at the YouTube. And it's just always the same. So a pole appears in front with exactly the same coefficient. And so there's almost nothing to say. So that's why I'm never putting the pole, because it's always easy to put back by hand. But definitely, the resurgent function is a pole and a log.
I see.
All right, so here we have Borel summation, and now, of course, it's a triviality to plug this expression in here. And once I do so, the integration, the Laplace integration, is easy, right? Because all I have to do is basically, I have jumps because of the log, so that's quite easy to obtain. And all these guys will appear. So, I mean, just you can fill in the details at home if you want, but I mean, I think it's almost, if I can just grab, this is quite a small blackboard on the iPad. So we can easily obtain that as the resummation at theta plus is equal to the resummation at theta minus. So basically you do the difference between left and right Borel resummations such that, you know, when doing the Laplace, oops, no, that's not what I mean. When you're doing the Laplace integration around these guys, you just get the jump of the log, so that the integral is really easy to do. And what you get is basically this. And if you assume that there's several omegas, I'm going to sum over several omega, because I could have several singularities, that's all I'm going to get. And then you say, okay, so that's a formula that I've already seen, because now I'm going to just re-understand this formula, basically calling this guy here minus the negative resummation. That's just convention. So it's just wherever you take the integration because of the jump of the log, so it doesn't matter. Discontinuity along theta. And so you got your discontinuity for free and your Stokes automorphism also for free once you've defined which we had already seen, but in any case. So I'm just telling you how you get them for free once you are in this class of simple resurgent functions. And of course, the automorphism is just related to the discontinuity in the obvious way, right? So discontinuity of theta is equal to the identity minus the Stokes automorphism. And so that comes up straight off without having to, which we postulated previously and we discussed a bit. This is now just coming straight off by the assumption of simple singularity. So the immediate thing you see, of course, that we have already discussed before, is that the perturbative series is not enough. If you start with perturbation theory and start moving around the Borel plane, there's going to be discontinuity, and once the discontinuity comes up, then all these other sectors, which I've called psi here, will just come down to you. Now, a little bit more of things to look at is that here I'm discussing the discontinuity along direction theta, and that involves a sum over different singularities that I can have on direction theta. So I can sort of focus on the discontinuity. So I could call this directional discontinuity because it's along direction theta. And then I can focus on the specific contributions to the discontinuity at each singularity. And so I can write down, and the reason I'm going to do this is to go towards the alien derivation. So I could just write down that the discontinuity at theta is equal to a sum over all these omegas of the discontinuity of each omega, where basically omega is something which has argument theta. Oh, sorry, it's the other way around. The argument of omega is theta. So then we have all these guys and the discontinuity at omega is basically, and I should write phi because it's associated to a specific sector. Phi is basically given by this. Okay, and now we look at this object. This object is quite interesting. You can think of it as an operator because it's a linear operator. However, it can be turned into something nicer by introducing the alien derivation. So this is a linear operator. And so we're good. We're happy with that, but it can be made better because it can be upgraded to the alien derivation, which on top of being linear is also derivation, and then we are even happier. So let's see how to do that again in one or two words. So basically what the idea, I'm just going to say is that discontinuity at omega is upgraded to the alien derivative, and the alien derivative satisfies Leibniz rule. So, and it satisfies Leibniz rule in two different ways. So it satisfies with the usual product, let me write it like that, on power series. And it satisfies Leibniz with respect to convolution on Borel transforms. So that's why it's so useful. I mean, it basically satisfies Leibniz everywhere. And we've also already discussed, and I'm not going to go into that definition, that if I have some direction on the complex plane with singularities, then the alien derivative is generically defined as some weighted average of possible integration contours that I can have. Weighted average. And so I won't give you the generic definition. I'll give you a slightly simpler definition in a second. So what I will do is to just see if I can. Okay, I'll just leave it like that. So let me put delta here. Weighted average. So there's a little bit of a notation that is required here that sometimes is a little bit puzzling. There's something that we can define which is called the pointed, or sometimes also called dotted alien derivative, which is a microscopic upgrade, just delta omega with a dot on top. And this is just basically exponential. It's just to include the exponential factor, prefactor, nothing else. So it basically changes almost nothing. But it's quite useful for two reasons. So the first reason is that if I just decompose the directional, and now I use an underlying line and saying theta, saying that I'm in direction theta. So if I just sum over all possible guys here, and all singularities I may have, then it turns out, and this I will use as the definition, that this guy is basically defined as the log of the automorphism. And once it's defined as a log of an automorphism, it's automatically a derivation. And for calculational purposes, if you want, you can play it a bit as well in examples. This is just given by, here we see the averages of somehow coming up, because I have to consider discontinuities of discontinuities, and so on. Oops. And that's the average that's actually coming up, etc. And you can see, again, I've already told you that there's a very good reviews by David Sozin, where he will give you as gory formulae for all these weighted averages as you might want. And if you want to dig more into the math literature, I recommend that you look into that. Okay, so now we have these objects working. So I think that what was the final objects that we introduced was the trans series. So let's jump to the trans series. Slightly more formal, because it will allow us. So, okay, so let me just say one more thing that you could say at this stage. That's okay, that's becoming slightly too formal, because now I also don't even have any idea on how to compute these things. How do I compute the derivation, which doesn't look like any normal derivation I have seen before? And so let me tell you how to do that. And that comes basically out of introducing trans series. So the trans series is the usual object we've seen. So let me just repeat it once again without basically saying anything else. I'll just be discussing a one parameter trans series. We will be discussing higher parameters in a second. For the moment, let's just leave it like that. So sigma is a trans series parameter, and phi n are my instanton sectors, if you want. And I'm just now saying a little bit more, is that all these guys are basically Chevrier 1. So I already know that that's already saying something about the growth that they endure, and they have the usual asymptotic series, which, okay, I can write once again. We've seen them many times, but fine. So this is asymptotic. I'm calling these guys G, FG. Okay, so all those guys will grow as factorial. And maybe there's a starting order and so on. So we've seen this, so there's no reason to discuss this a whole lot more. Now, the key issue, and I'm not going to show that for you, is that this pointed alien derivative, which we introduced that could seem a little bit ad hoc and falling from the sky, has a reason, because it has slightly better properties than the non-pointed alien derivative. So of course, they both are linear and they are derivations. But here's the thing, which actually makes everything go through, is that the pointed alien derivative satisfies the following commutation relation. It commutes with the ordinary derivative. All right. So now we can try to deduce a way to compute it, because we are going to assume, this is basically, I think, the original problem that Ekal was addressing, which is we're going to assume that we have a nonlinear ODE. Let's assume it's first order. Why? Because we're just playing with a one parameter trans series. So I have a single boundary condition, a single initial condition. So let's assume that it's first order for the sake of argument. Of course, you can do all these things for a more complicated slip. I'm just, again, trying to go slightly more formal, but yet without trying to be very complicated. And if I do that, then because, you know, the pointed alien derivative commutes with the standard derivative. And by the way, I can write a triviality, which is that the derivative with respect to sigma commutes with the derivative with respect to z, with sigma being the trans-series parameter. So this, of course, is obvious for everyone. The thing in white may be less obvious, and you really have to play a little bit with Borel resummation just to do the proof. We're not going to do here. Then there is these two objects, basically this guy and this guy. They satisfy the same equation. This is just, if you want, the perturbation to the nonlinear ODE. And so they will both satisfy the very same first order linear ODE. And because the space of dimensions is one dimensional, this means these objects need to be proportional to each other. In other words, so because of those two commutation relations, these two objects have to be proportional to each other. So basically, I grab this equation very simply. And what is the constant of proportionality? It's going to be some number. I'm going to put an arrow here because it's not the same number that appeared in the Borel. It's not that number in the Borel singularity. Where was the Borel singularity? So it's not that number. And as I've said, if you look and read the notes, the fonts are different. I just can't draw the different fonts, the same letter. But I'll put an arrow because even though we're in one dimension, when we go to higher dimensions, it's going to be actually, we'll have a vectorial structure. It can't depend on z because that's just, that's the variable of the differential equation, but it could still depend on sigma. And so this is quite fundamental equation, which is known. So now we don't care about where it came from. I already slightly derived for you. It's called the bridge equation. Because it's providing for you a bridge between alien calculus and standard calculus. So you could say, well, I don't know how to take alien derivatives. That's fine. I know how to take derivatives in sigma. It's derivatives with respect to transverse parameter. It's still just standard derivatives. So there's really not a big mystery there. So I'm sort of okay. Now I know how to.
Can I ask a question?
Yes, please ask questions at any time.
Could you just explain more about why the commutator of dotted derivative and dz is 0 because this dotted derivative depends on, there's an exponential minus omega z, so I don't understand why the commutator is 0.
That's actually, so yes, so I'm not going to do the derivation for you. So the fact that the dotted alien derivative, where did I define it? So the fact, so as the question was saying, there's a very important part, which is that this guy is there. So if you were to try to compute the commutator of the standard alien derivative with regular derivative, and if you try to do this by analyzing, an object where it can apply, so a Borel transform or wherever it happens, you will see that the commutation will not work. So this is actually quite relevant if you do the calculation with trying to take the derivative with respect to omega and derivative with respect to z to some object that you Borel resummed. It will be quite important that this guy will be there so that the commutation relation works. So it's not, it comes more, if you want, as part of the need for the failure of this guy to commute with the standard derivative than anything else. And that you could see.
Okay.
Actually not sure what was the motivation from Ekal back in the 80s, if this was naturally introduced like that or not. But definitely, if you just try to do the commutation with this guy on a Borel resummed function, you will see that it misses to commute by this guy, and then it is very natural to immediately introduce the pointed alien derivative. Okay.
Thanks.
I'm trying not to do all the calculations. So I mean, if you can't do the calculation by yourself, please just write me an email, and then we can discuss it in private.
Can I ask a question? Sorry.
Yes, please go ahead.
What happens if we have a second order differential equation or a third order? Do the delta omega and d phi d sigma related?
So, well, the first thing that you can do is that if you're just standing within the framework of ODEs, I mean, higher order ODEs are really basically first order systems of ODEs. So I just can reduce everything to all of this, and basically the yellow guys, the yellow proportionality constants become just vectors. But we'll discuss that later. So that's
okay.
And please keep asking questions at any time. So what was the last thing I wanted to discuss is exactly, so these guys, S omegas. Sorry, I have to go back to this. I want to know what is this guys equal to. I'll keep using the vector here, even though I already sort of gave it away that they will become vectors when we get to higher order at these. What is this equal to? Because it's still a function of sigma. So at first you could worry that it's an arbitrarily complicated function of sigma, but it actually turns out that there's a very simple argument. Again, let me not go through all the details, but let me quickly run through it. Is that you can sort of naturally do a transmonomial of this type. So with transseries parameter and with exponential factor, you can associate naturally a weight, which is just the sum of n plus m. And if you do this, you can sort of try to see basically by homogeneity, what must this proportionality constant be? So this is sort of a weight. And it's not too hard to see two things. So let's see. The first thing that we can see is that, so delta, the alien derivative with k instant on action. So let's go back to the dotted alien derivative, which in fact we were just discussing because of the exponential. So it will have the dotted with k guys will have a k there, k times a. So this makes the weight jump. M goes to m minus k. And if I just take the standard, the sigma, this makes and of course the sigma is just removing a sigma, right? So there's nothing to say. It makes the weight jump from n to n minus 1. So these are the two natural objects. They appear on both, so this guy and this guy. We're seeing how they're scaling with respect to this weight. The transseries itself has weight 0. So the weight of the transseries is 0. And that's just where did I define the transseries? Here we go. So we could put this thing. So there's an n there and there's a minus n there. So let me remove those. So then we have an object which removes weight by k. We have an object that removes weight by 1 on guys that have weight 0. So this basically constrains the weight of these guys so that the homogeneous property of the relation is upheld. So we can conclude that the weight of S has to be 1 minus k. And so S at the singularity Ka is actually given by Sk, and I should put arrows on everybody so that we remember what they are. 1 minus k. And so I finally get the final way in which I wanted to write down. Oh, what happened here? Oh, I took the wrong pen. Sorry about that. This is the pen I want. So delta Ka dot phi that sigma is going to be equal to Sk. Now those are just numbers or vectors in the higher dimensional case, but fine, times sigma times d phi is sigma. That's sigma. Okay. And we further expect two things that are just motivated by what's on the blackboard right now. First of all is that, well, that's k different from 0. I'm just because, you know, Borel. So this, remember that the alien derivatives are encoded in singularities on the Borel plane. So there's no singularity at the origin. And the second thing that I'm expecting is that k is smaller or equal than 1, because there's no reason to believe that there's going to be any singularities in sigma. And so basically, this leaves me with a bunch of numbers to understand, which are these numbers. And so I really need to know all these numbers if I want to, you know, have a complete solution to my problem. And there's many names for these guys. They sometimes go under the name of Ekal analytic invariants. The most common name to use is, of course, Stokes coefficients or generalized Stokes coefficients. If you just, I mean, from classical analysis, that would be the Stokes coefficient. So these guys can also be sometimes go under the name of the nonlinear Stokes data. So this classical analysis is linear. And so these guys would all be the nonlinear completion of that. And the reason why they're called sometimes analytic invariants is because if you have two apparently distinct ODEs, but they have of the same order and so on, you're not absolutely sure if they're the same. One way that you could know that they're the same is by saying that they have the same analytic invariance, the same Stokes data. So which also, by the way, might be a very hard problem to do, but in any case. So that's the sense in which they're invariants. And another formula that I might want to write is that if you just come here to the bridge equation and you plug in the trans series, where was it? Here we go. So if we grab the trans series here, which has sectors phi n, and we plug it into the two sides, so actually I want to do the other one, the two sides of the bridge equations. So then it's not very hard to see that we're going to get bridge equations directly for the n sectors. And so that's sort of you can put both of them here. That's the final formula I want to write, is that you can write this expression for the phi n sector is going to be this guy times n plus k times phi of n plus k. And you see, that was a formula that we saw last time, which was sort of motivated by the example that we're studying, but which sort of fell from the sky. And now, okay, I did say that I would derive this for you today, and now here we have a little derivation. Okay, so basically, you know, even though we introduced this weird object, this alien derivation, the truth is that here we have two formulae to compute alien derivatives acting on the trans series or alien derivatives acting on the trans series sectors, and it's really not that hard. So it's actually quite simple. Of course, we have now managed to compute all alien derivatives up to Stokes data. So let's discuss a little bit Stokes data. Stokes data, and basically, again, I will just very simply review two formulae that we also had discussed previously, motivated and so on, and now we see that the derivation is quite simple. So recall that we had this object here, the Stokes automorphism. And that as an automorphism, it was, or it is, the exponential of a derivation, and the derivation is the dotted directional alien derivative along direction theta. And this is an expression that I already in the first time when we were discussing the partition, the Bessel, quote unquote, the Bessel partition function. And we were discussing this, it's Stokes jumps, and I showed this plot that I assigned as a homework to do all this. I remember, I don't remember if it was 6 or 8 turns around the origin, this monodromy. I don't know if the students try to do it or not. But anyway, so today I will make the Mathematica notebook available, because today is the last thing I want to challenge students with. And then I'll put the notebook available for you guys to see possible solutions. I mean, by no means this is the best way to code it. I mean, of course, there's millions of ways to do it. Anyways, so we saw this formula already when we were discussing the Bessel-Stokes jumps, and it looked probably a little bit mysterious. So can we try to understand this in a slightly better way? And well, yes, actually, because let's consider that we're going to have to look at the Stokes automorphism along 0 for our 1-parameter trans series. I'm still in the, where did I write it? I'm still in this example where I'm using the trans series. It's 1-parameter trans series, which looks like that. Basically, there's not a whole lot to say. And by the way, maybe I should say that I'm assuming that of course, is an assumption that I didn't spell out, but sort of implicit. I'm assuming that A is real, hence there's a singularity on the possible axis, which is the one that I am dealing with right now. So I am looking at that singularity on the possible axis, and what can I do? Well, I just write a definition, which was just there. And what did I gain? Well, what I gained was that I now know, as I've just said, that there's a single singularity on the possible axis, which is at instant on action A. So I know that this is just delta at A, nobody else. And the reason why there's nobody else is this root that we've already discussed. So there's just A. There's just, if you remember the motions we discussed last time on this alien chain, there's just one forward motion. Of course, I can do it multi-step, but there's one only elementary step motion. Okay, so that was not hard. So what can I do next? Well, next, I can just use the bridge equations. What were the bridge equations? Here they are. So if k is equal to 0, I'm sorry, if k is equal to 1, that's not what I meant. K is equal to 1, so that guy goes all the way. So that's k equals 1 is what I've just sort of tried to kill, where of course here there should be a 1. So let's just put it there. This is not very hard, right? So this is just exponential of S1, dd sigma, it's not gonna fit, sorry, but let me do it right in the next slide. It's gonna be exponential of S1, dd sigma of 5, z sigma. But this I know how to do. It's just the shift operator. It's just a translator operator. Aha. So now you look at the beginning and end, you say, this is very interesting because I just recognized a formula which is quite familiar to me, which is the standard Stokes phenomenon. And now Stokes phenomenon is a direct consequence of the Stokes automorphism and the way the alien derivative plays in the bridge equation with the derivative with respect to dd sigma. So now it's ultra simple how these things come by. And of course you could say, well, this is an example that I knew how to do it in any other way. That's true. But well, the first thing that we're going to discuss is that I still haven't addressed the pi direction. And the other thing, which is obvious, that, yeah, sure. I mean, in a simple case, everything is simple. In harder cases, it's probably good to have more powerful machinery. So as I've just said, we've discussed the case where k was 1. But now we have all the negative k's still to address. So along the pi direction, it's really a mess. So what happens if instead of trying to compute the Stokes automorphism along the 0 direction, I try to compute the Stokes automorphism along the pi direction? Well, things start getting nastier. I do the same game. So I write this as phi, like that, of phi of that sigma. But now there's not a single guy. So I'm trying to put both blackboards, both calculations on the same blackboard. So now there's not a single guy. Now, because, well, in principle, so again, I mean, then you have to go problem by problem, seeing what happens. And not today, but in the last lecture, I will show you non-trivial Stokes data, forward and backward Stokes data for polynomial equations. And you'll see that it really, it's basically infinite set of data. And it becomes really a mess. Well, I mean, we've organized and tabled it in a way that it's quite compact, but if you just disentangled it, like the way I'm showing it to you right now, it's a mess. We will discuss how to quote unquote compactify Stokes data in the next lecture. So now, as I said, there's not a single guy. So there's all these negative guys. So I need to take into account everybody here. So when I do this step of the calculation, which along 0 was easy, along pi becomes, let me see if I can put everybody here, exponential of the sum, and delta A, where n goes from 1 to plus infinity of phi of that sigma. So, okay, that's harder. And now the next step is to translate from alien to standard derivative by the bridge equations. But of course, so that's the next step I want to compare. And the next step is just saying that I have an exponential of all these s's that appear with this power sigma. So you see that I'm really generating a quite complicated automorphism now. And I will just write it like this, the final step. Now I really need to have knowledge of what the s's are so that I can actually do the integration of this vector field flow. So this I will just write as phi of z, and I will call this function as pi of sigma. Okay, so you see that now this guy, instead of being just a simple shift as it was on the forward direction, quote unquote forward, in the quote unquote backward direction, I have an automorphism that I still, you know, I need to study what is the 1 per meter flow of this of the formal vector field that I've just written for you. And so I really need to have knowledge of Stokes data, of what all these s's are. By the way, I just realized that I have been putting arrows on top of these guys, and I've stopped putting arrows, but maybe I should have put in an arrow there, just for if anybody is looking at these notes at some stage to see that they're all consistent. And you could say, oh, but that's so nasty. Why do I care about that? And again, because you know, if I really want to go everywhere on the complex plane and really understand what this trend series is as a function on C, sooner or later I have to cross one of these lines. So it's very fine, and that's what people did for a long time. It's just I just crossed the zeroth line, and I don't worry about the rest because that's the easy line. But I mean, if you really want to, for example, compute the monodromy, you really need to go all the way around. So you need to cross the pi line at some stage. Anyways, this is the complete information about the function. Let's see, what else do I want to say about this? That's probably about it. So the final thing I want to say is just to say that these arrows. So we've also discussed this in the last lecture, which is that there's Stokes data, and Stokes data. Let's just so Stokes data are these guys here. So the coefficients which appear in the bridge equations, and they of course translate to the connection formula. That's why it's Stokes data. If you go back to Stokes paper, you know, the two boxes in pink is what's, you know, in the original Stokes paper studying the area function, not written like this, of course, but implicitly it's what it is. Just telling you how there's a Stokes coefficient of the area function that can turn on when I go to the negative real axis. Well, it depends on the conventions. Okay, whatever. So that's a Stokes data. But when you look at singularities, Borel singularities, when we define the simple, where was it? The simple resurgent function. So those guys are Borel residues. These guys are really numbers, always. Even in higher dimensional cases that we will study. I think we have 10 more minutes before. So we'll look at them after the break when we discuss higher dimensional cases. So what's the relation between these vectors, which for the moment are still not vectors, but will be in a second, and these numbers, these complex numbers? So let me just write one simple formula, and then we can do the break. And then when we do the higher dimensional case, it's the formulas are slightly more involved. So Stokes data and Borel residues, they of course encode the same information. We'll see in the second part of the lecture that Stokes data are somehow more fundamental than Borel residues. Okay, for the moment, let's just write down the formula. So let's rewrite the Borel phi n now for our specific trans series, and let's expand it around the singularity, the kth singularity, and this is a simple resurgence function. And so what I will find is going to be the resurgence of the nth plus k sector. Again, I'm not putting the simple pole, it's always there, it's easy to put back in. Fine, n plus k, s minus a, and then there's the log. I am also not writing regular terms, of course, that this expansion has the singular terms and then it has a bunch of regular terms, which we just don't care. And so we have these guys that we want to relate to those guys. And so the first thing that you observe is that these guys, they just depend on k, on what order of singularity I'm looking at. And these other guys, they depend on starting node and where I finish my ending node. And so they sort of have more structure, which is required. So it's not very hard. So let me just schematically, I don't think this calculation is worth doing. So again, it's written here in the lecture notes, so you can take a look, but I'll just mention it schematically. How do you relate both, just for completeness? And so it's not what you want to do is to compute the discontinuity. You can compute two things and then you just match them. Compute the discontinuity, which we've already seen many times. So let me just write this formula. And then we know that the discontinuity relates to the alien derivative. It was just an iteration. The alien derivative, the dotted alien derivative was just an iteration of discontinuities. So I can write down, let me just, okay, it's enough to just look at these two things. So now a quick reminder that that guy was basically minus the discontinuity and then kept iterating. And so you just plug one into the other and eventually you'll find, I will write one formula and I won't write more. Then you can compute delta Ka. I'm already taking the dotted out by just removing one exponential factor so that you can see that it appears. And this is going to give you, so let me just write this formula so that you get a feeling for what's going on. So there's a sum of, well, let me not give you all the details of the sum. You can just plug them in by yourselves. It's not too hard. Times, I should try to see if I can fit everybody here. And I go just jump by jump, all combination possible. Well, a bunch of guys to n plus k times phi of n plus k. And now basically you just have to, so let me choose another column. So we started off with this guy that came from the discontinuity. Then it appears everywhere here to build this guy. And we get basically all those guys there. And so this gives you a relation between Stokes data and Borel residues. So this is not too hard to find. Yeah, I guess I can write one formula. Just I don't want to be writing too long formulas, otherwise it gets ultra boring. So I'll just write this one formula that comes out immediately, which is this one that you can sort of obtain. And similar formulae for along pi, which are more intricate and they really there's probably not a whole lot more to say. So let me just give you another, let me just share something else for a second to give you sort of, what do I want to share? I want to share this. So this is the physics reports, the lecture notes that we're following. And so I was just discussing stuff which is here on Appendix A. And I'm giving you this homework reading assignment, which is this part of, I mean, of course you can read what's before, which is just what I just reviewed now from the lecture notes. And then there's an explicit linear example, which is done afterwards. And I would suggest this for the students as a reading assignment, because what this is going to be doing is following sort of the spirit of the linear examples and that we discussed in the first lecture, which was the Bessel case. It's slightly upgraded from the Bessel case because now I'm looking at a trans series. So the Bessel case had basically a plus exponential and a minus exponential. And here I'm looking at the perturbative, the minus exponential, and the plus exponential, so that the Borel structure is slightly more intricate. Here you see the perturbative guy has a A1 and a minus A2. That's the one instanton. Well, I shouldn't call it, that's the minus instanton, the plus instanton. And everything is worked out here now in this more formal language that I just went through. So I think it's very easy to follow just what's written. So I would recommend this for the students as a reading assignment. There's basically almost no calculations to do. So I think we still have 5 minutes to go, but unless the organizers complain, I think probably now would be a better time to do the 15-minute break instead of waiting 5 minutes, because I want to jump to higher dimensional cases next. And so there's sort of there's really no point in discussing higher dimensional for 5 minutes and then doing the 15-minute break. So maybe we can.
Okay. It's up to you. So we may start the break. So 15 minutes breaks. Yeah. Starting from now. Okay. Break.
I'll be around if anybody has any questions. So just I'm here.
send an email to courses. I'll write it on the chat. Courses at IPhT.fr. Maybe not today, but at the end of the last lectures. And I'll prepare the certificate and send it to you a PDF. Okay. On the chat. So, okay, and, I guess that right now we are at 14 minutes, more or less. So, okay, you can restart slowly. Maybe you can start with the recap, I don't know. So it's up to you. I switch off.
Okay, all right, let's share the iPad. Restart. Okay, here we go. All right. So what I want to do now in the second half is to discuss two things. Let's go. One thing I want to discuss is what types of transmonomials one generically finds. So we keep talking about this exponential of -1 over h bar, which is the standard instanton contribution in quantum mechanics, but more things can be found. So I will very quickly go through it just to give you a glimpse on how generic all these structures are. And the other thing I want to also go through is what happens to higher dimensional problems. By higher dimensional, I mean more trans-series parameters. Generics. Okay, so that's the two things I want to do now. All right, so let's start by discussing transmonomials, I guess. So one thing, and already Ricardo already made that question, is what happens if instead of having a first order nonlinear ODE, I have a kth, not sure case, okay, yes, kth order nonlinear ODE. What shall I do then? Which, by the way, is what's going to be generic if you're looking at multi-critical string theory, minimal string theory, whatever. So I mean, when you're going in, and I will discuss this in the next. Well, I was supposed to discuss a bit of this today. I doubt it. But in the next lecture, I'll discuss this a little bit. When you're looking at the KDV hierarchy, the string equations you get out of the KDV hierarchy are higher and higher and higher orders. So what shall one do in that case? And so of course, we expect to find monomials all the time, or monomials should still be there. We can call M. And now I'm going back to X, so X is small. But there will also be transmonomials, which I'll call T. And I still don't know exactly what's the class of all possible transmonomials I can find. So one transmonomial that I do know that I can find is that we've been discussing a lot so far. What else can I find? Let's try to understand this in well, one generic statement and 3 examples. So the generic statement is the kth dimensional case. So the kth nonlinear ODE, kth order nonlinear ODE, I will write it vectorially as basically a rank K system of first order nonlinear ODEs. Okay, so let me just write the system. It's easier than the sentences. So it will look like that. Okay, and it's nonlinear, so phi can be an arbitrarily complicated function. Now it turns out that, so I don't want to go through all the details, but it turns out that you can generate, I mean, I think it's pretty convincing that you can sort of, well, let me call it quote unquote linearize the system, or more formally, what's known as writing the system in prepared form. And prepared means prepared to do a trans-series analysis. That's, I think, the origin of the name. In which you can do, well, you can think of it as a linearization, but it also involves, generically, it involves a transformation of variables, that you can rewrite the system always in this way. It's 1 over x squared. There's a matrix. I'll come to this matrix in a moment. Times u plus 1 over x. There's another matrix times u plus higher order stuff that I will not care about. And A and B, it turns out that A and B are diagonal matrices. And whoops, can I put everybody? Yes. I'll write them like this. These are the diagonal components of these A and B matrices. And now if you just decide to truncate and say, okay, let me see to leading order, what do I have here? Well, what I have here in prepared form is basically a linear differential equation that I can solve. And if you solve it, of course, you do it component by component, but it's not too hard to see that in prepared form, the solution, component by component, the ith component is going to be of this form. So there's going to be a parameter because it's a first order differential equation. And then there's going to be a term x raised to the power beta I that comes from the B matrix. And then there's going to be a term AI of x that comes from the A matrix. And so you see that these are the components, the transmonomial components that appear generically when you're trying to solve a kth, what was it? Yeah, a kth order nonlinear ODE. So it's not too hard to convince yourself that those are the things that are going to appear. And so you sort of convince yourself that the monomials are indeed, as I wrote, of the type X. And now you can say that on top of all these monomials, there's a bunch of transmonomials, which are of this type. And I need to get monomials and transmonomials together into a trans series. To solve these more general problems. All right. So, I mean, if I write down now the trans series ansatz for our problem, still in vectorial form, let me put vectors on top of everybody. So now everybody is indexed as elements on a positive lattice. And it's going to look like this. This is what the trans series ansatz looks like. Of course, when I write beta vector, I'm just thinking of the diagonal of what was the B matrix as becoming a vector. And then the same thing for the diagonal of the A matrix. So I'm taking these guys to make another vector times the non-perturbative sectors.
I have a question.
Yes.
If I understand correctly, if you include the dots, the term you neglected, you somehow deform the monomials, the transmonomial.
No, we'll come to to extra transmonomials in a second. What I'm just saying, you know, what's in yellow on the blackboard is the solution. That's it. What I'm telling you is that
of course.
Dots, I need to include all these powers of the solution. That's what the trans series is. So you see that here, I now have powers.
Okay, I understood. Okay.
Powers. All right, and just so that for completeness of notation, let me just say that this is basically just the product of all these guys, sigma 1 and 1, sigma 2 and 2, and so on. I guess it's k of them, sigma k and k. All right, so looks okay, and those asymptotic sectors are, of course, by the way, I keep forgetting arrows, so are all the standard things that you already have seen 1,000 times, so it's no mystery here. So just going straight off k-dimensional seems not to be very complicated. I basically do the natural, in this case, k-dimensional generalization of what I had, and I can play this. So you say, okay, this so far looks good. Are these, well, these are the monomials, we sort of know that's it. Are these the only transmonomials that I can have in the game? So that's the second question you could have. Could I have different transmonomials? And if we're doing this game with looking at differential equations as examples of what might be, and of course, I mean, you could always argue that when we're doing functional integration, we would get more weird stuff. And you can ask what other weird stuff could be there that it's at least motivated in simple examples. So let me now show you 3 trivial examples of things which are off this class of transmonomials, and then we can classify transmonomials. Okay, so more transmonomials. So let me write down for you 3 trivial examples of differential equations I can just write now. In 1 dimension. I mean, I'm just motivating examples just so that you see things appearing. So here's a simple equation that everybody knows how to integrate, and the solution looks like that. So of course, if n is positive, there's really nothing there, but I didn't specify what n was. So if n is smaller than -1, then I get new stuff, new transmonomial. I don't know. Okay, you'd say, yeah, sure. I mean, I can sort of be convinced that stuff like that could appear. So it's not a huge surprise that it's, on top of exponential -1/x, I can find exponential -1/x squared, -1/x cubed, and so on. Yeah, that's interesting. So those are very natural transmonomials that you could cook up. More. Can we have more stuff? Yeah. How about if when I write down my simple example of a differential equation, which might have something new, what if I already include a transmonomial in the equation to start off with? What's the solution? Well, again, this is very simple differential equation. Of course, I'm not choosing these examples at random. I'm choosing example that you can trivially solve in 1 line and be convinced that these things naturally can appear. About that, exponential minus exponential of 1/x. Whoa, that's something new, right? I have an exponential of an exponential. So okay, so that's a new transmonomial that I don't know if you could guess. This is certainly a new transmonomial. which are more rare to find in physical applications when we start seeing all these exponentials of exponentials. More stuff. Is there any other stuff? So there's one last illustration I want to make. I'm not doing example 1 through example 1000, just 3 examples. And then I think we can sort of grasp what's the generic thing. So here's another transmonomial that we've seen before, log. What if it appears already at the level of the equation? And again, you guys can all solve this easily and find new transmonomials. There's logs appearing. Log x divided by x.
Can I ask a question? Sorry.
Sure. This was my last example.
So maybe it's a naive question, but is there a notion of orthogonal basis between transmonomials, just like we have for simple monomials? For example, we can construct orthogonal polynomials and so on. Is there something analogous for transmonomials? Or?
I wouldn't call it orthogonal because I don't think the concept would make sense. But if you want to say if there's a basis of transmonomials, is what I'm going to say next, basically. So I'm going to transmonomials that you can get, but not with the orthogonality or orthonormality.
I see.
All right. Okay, but okay. So hopefully, I've convinced you that there's natural things that appear. So that guy, and that guy. You could ask, are there more? So I'm not gonna classify them. I'm not gonna prove theorems or anything. But, so basically, this is all there is in the following sense. So now we can classify these guys. So I'm just gonna give you the results. So the first thing is that monomial. Nothing new to be said here. Actually, that's it. And I'm even going to say alpha could be some real number just to be as broad as possible. So what is a power series? It's just a sum, a formal sum, infinite formal sum of monomials. And I'm going to call, unfortunately, again, when you write LaTeX, you have so many fonts to play with and you think you're really smart in using all these fonts. But then when you have to write on the blackboard, you realize that you're really dumb because it's another S with another font. Anyways, sorry about that. And so power series are going to be sums. Maybe I should actually put that S here. And they're easy to order. So there's an ordering concept. Otherwise, how am I organizing my power series? I organize it by just saying usual. So what I'm writing here is basically trivialities. Okay, so that's it. Remember that X is very small. And so, yeah, okay. So power series are easy because they're just sums of monomials. So I'm expecting trans series to be sums of transmonomials. So the first thing I should be able to do is say what a transmonomial is. And so this is going to be a slightly circular definition. I don't want to be going into all the gory details of math. It's just mostly to convince you. So there's a monomial there, and then there's an exponential of a power series. Okay, so alpha is real, and S of X could be anything. So it could be, so I'm just going to write it as power series, which of course could be convergent, could be just a monomial, could be 1 over X, that we've seen, or could be a trans series itself. And that's why I'm saying that it's a slightly circular definition, but let's just assume that S could be arbitrarily complicated power series. And now there's a subclassification of the transmonomials, so that we need to do it in 2 steps so that we get the whole picture. And so the first thing that we're going to define is, remember that before, out of monomials, I constructed the power series as a sum of monomials. So out of transmonomials, I'm expecting to construct a trans series. Let me put here trans series, which, well, it's a curly T again. I will be more careful in the future on how to define these things. It's going to be a sum of transmonomials, infinite sum possibly. Transmonomials. And I'm going to start by putting a caveat here. As I said, there was a slightly subclassification that I'm going to call it a log-free, because I have not put anything with logarithms yet. So I've put exponentials. I have not put logarithm. So we have a formal sum of transmonomials and their respective powers. The logs will come in a second. And then you could say, well, if I have this infinite sum, I would like to order it somehow, the same way that the power series was ordered, the obvious way. So how do I do the ordering of the transmonomials? Basically, I do it lexicographically, which means that I do it in 2 steps. So let me just put the what was the color I chose? Green. So now we say that x to the alpha exponential of minus ax will be much smaller x to the beta exponential of minus bx. Remember that x is small, blah, blah, blah. If and only if a is much bigger than b, or that's what, as I said, is going to be lexicographically because it's in 2 steps, or if a equals b and alpha is bigger than beta, which is the previous case, right? Because then the transmonomials just basically, they don't matter. And now I also have an ordering, and I can write down my trans series. So as you can see, out of monomials, I sum them and I have a power series. It's ordered perfectly fine. Out of transmonomials, I sum them and I have a trans series. Again, ordered perfectly fine. This is not yet the most general case. It's almost the most general case. So let's now discuss the most general case, which is the general transmonomial. So I had a transmonomial T was written in that way, just for you to recall. The general transmonomial also can have logs. So I need to do this in 2 steps. First, I introduce this concept, log m of x, which is log of log of log of x, m times. So I'm iterating logs. By the way, in a sort of similar way to what we've seen up here, where I was iterating exponentials, and I will soon iterate arbitrarily many exponentials. So general transmonomial, I can iterate logs where, well, it goes almost without saying that m must be an integer. Otherwise, I cannot just do fraction iterations of logs. And so what I do for a general transmonomial, I grab a transmonomial, in the sense which I have defined earlier. And the sense which I've defined earlier was this way, was S could be a power series, but it could be less than a power series. It could be just a monomial as well. And then I replace some of the x's with replace some of the x's with log m of x. Okay, and this will lead to the general transmonomial. Can I have, yes, I can have everybody here. So that the general trans series is then a sum of general transmonomials. Okay, so that's sort of the classification we have and the definition. And now there's 2 things that we can see that can be occurring in this way, is that I have stuff that appears in a general trans series, exponential of exponential of exponential. I can have arbitrarily iterated many exponentials, and I can have log of log of log of log, arbitrarily iterated many logs. So you can see that these quickly become, beast things. We can call this arbitrary exponential height an arbitrarily logarithmic depth. Of course, I'm calling height and depth because of the relation between the exponential and logs, but these are just names anyway. So I can construct with transseries involving these arbitrarily horrible beasts. And you can see that the class of functions that I'll be able to describe using general transseries is quite large. It's truly huge. Of course, physical examples don't see arbitrarily height exponentials nor arbitrarily depth of logarithms so far. Who knows if there's examples to be uncovered that will have more of this stuff. So for sure, double exponentials have been discussed a lot in the case of SYK, but I mean, those can be sort of treated from the point of view of the matrix model as just a simple exponential. So I wouldn't say that it's really a new transseries appearing. So this is what general transseries look like. All right, and of course, as I just said, we're mainly going to be interested in just a single exponential and a single log, and that's it. But I hope that I sort of convinced you that things can be made arbitrarily complicated. All right, so what can we do with a single exponential and a single log in k dimensions? So that this is sort of still not done. All the generic discussions we need to have. And because basically another thing that we'll see when we discuss applications is that pretty much nothing is a one parameter transseries. Everybody is multi-parameter. I mean, the simplest example that you could have of this minimal strength theories is already second order differential equation. So already it requires two transseries parameters. So nothing is really a one parameter. So you have to be discussing these k-dimensional cases all the time. All right, so that's the sort of the last thing I want to say before going into examples is what happens in general dimensions. So, and now here, okay, let me put the title here. Multi-parameter transseries. All right, so multi-parameter transseries, they could have, let's say that it's the example we were doing before. There were k instanton actions. So I'm going to organize the vector of instanton actions in this way. And we already wrote transseries for these objects, but now let me write them again, being slightly more precise, because this is actually going to be quite important for string theoretic examples, is that for the moment, to start off in a sort of slightly simpler setting, I'm going to consider something which I will call, and this will become clear in a minute, the name, but for the moment it's just name, the non-resonant case. And the non-resonant case means the following, means that all these instanton actions that I've written up here for you, they are linearly independent over the integers, which is what's important because that's what appears in the argument of the exponential. In other words, there is no vector that could appear as a multi-instanton sector such that this inner product is zero. So if you want, another way to write this is that if I write now and now let's just write it in this way, my transseries. So I sum over all these sectors. This term which appears here in the argument of the exponential never vanishes. So it's always, no, that's not an arrow. The arrow is here. This term in the argument of the exponential is always either exponentially suppressed or it could be exponentially enhanced, but it never vanishes. So that's the reason why we are introducing this little caveat. Why is this important? At several levels. Let's discuss. What are these sectors that we have here in the transseries? These are all the asymptotic sectors. Well, let me not write the asymptotic series for the thousandth time. You guys already know this well. They're labeled, all these sectors, by a vector in a lattice, in a semi-positive lattice. The semi just means that the perturbative sector is also there, right? So it's a k-dimensional semi-positive lattice, and I will many times be illustrating this with a two-dimensional example. So let me show you just what these things might look like. So here we have a two-dimensional lattice of trans-series sectors. I have here my perturbative sector, oops, down here. And hence the semi-positive, there's the sort of the 1-0 instantons, the 0-1 instantons, and then there's everybody else populating the whole two-parameter trans-series. I'll come to the arrows in a minute. It's just so that you have in your mind just these two-dimensional semi-positive lattice. Let's go back to the iPad. Okay. And so on. All right. So there, as I was saying, all these phi n's, all these asymptotic sectors in the trans series, they're labeled by an integer. And now you ask, where are Borel singularities for this problem? So I'm assuming that everybody is Jevre1. We already discussed that. That's the class that we're interested in. Where are the Borel singularities? Well, that's also not too hard to convince yourselves where they likely are, because when we discussed, okay, so I can right here, when we discussed the discontinuity in the previous hour, well, okay, maybe I can try to find, if you just bear with me for a second, where was that formula that we discussed in the previous hour? There was a formula for the discontinuity. Here we go. So when we discussed the discontinuity, we saw that the discontinuity along some specific, well, this one is even not the one I wanted, really. This is the one I want. The discontinuity along some specific direction sums up all the, the sectors that I can see resurge along that direction, and the weight, they come with exponential weight, and the weight is precisely dictated by the singularity. So now I just reverse engineer what I said. If I start with a trans series, I expect the singularities to be at this weight. So we can now go back to what we're doing. So the natural place to assume that, where is it? Here we go. We have the trans series there. Where are Borel singularities? Well, the simplest thing I can assume is that there S is the instanton guys. I could be sitting in a random instanton guy, and I have to look back to all the people that were behind me. So just to have a picture associated to what I just said, look again at the lattice. And so here we're sitting in the 3-2 sector. I will come to give you in more detail what I mean by sitting in the 3-2 sector, which I just highlighted in blue. And you can see that there are people ahead of it, like the 4-2 or 3-3 or whatever, but there's lots of people behind it. So I really have to assume that there are possible singularities behind me. And that's the reason why I'm saying that singularities, where's the iPad? Here it is. That singularities are labeled by integers, not semi-positive integers, but arbitrary integers. All right, that's where I'm expecting singularities to be. So let's just be slightly more concrete and define a projection map that grabs a possible sector in this lattice and gives me a singularity on the Borel plane. So to the elf guy, I get a singularity located at a.rl. And because I am in this non-resonant case, what I know about this map is that it's got vanishing kernel. All right, good. So that's what it is. And now you could play the game that I've just discussed for you in the previous hour. Let me not play it again, in fact, because we're running terribly late. So let me just write down two formulae that I think need no motivation at this stage. And you say, okay, that is exactly what I would expect, is that Borel singularities are organized in this way. So I have my Borel residues that now change between sites on this two-dimensional lattice, or k-dimensional. I mean, I was thinking of the plot, but we'll go back to this, the two-dimensional example in a second. So I see the resurgence of the nth plus L sector. There's a singularity there, and then I have my log, guys. And plus holomorphic, blah, blah, blah. And something similar will happen for the bridge equation. And the bridge equation is now going to look like this. And now it becomes very much clear why I was putting arrows on Stokes data before. And now you can say, now this is very clear, because definitely Borel residues are clearly numbers. They're just proportionality factors at the singularity. These guys are vectors. And so they live on this lattice. I can think of these guys as living on the lattice. So this is what it is. Let me, actually, I think this is important enough so that I write it down. So I have a k-dimensional vector of Stokes coefficients. So SL is SL1, comma, through SLK. And so you're seeing that the complexity of really pinning down Stokes data, which is fundamental, as I said many times already, to go everywhere on the complex plane, is getting more and more complicated, because not only I have to find all these, in principle, infinite number of coefficients, which are generically hard to find, but they're also organize themselves in vectors, and I have to understand their vectorial structure. And so all this is quite intricate. Anyways, we will find them. Bear with me. Let's go back to the bridge equations, where you recall that in a one-dimensional case, I could just have a single step forward, and I could have arbitrarily many steps backwards, elementary steps, and I can, of course, compose those steps by taking multiple derivatives. But at the elementary level, there was a requirement. Let me write it here in gray, because this requirement makes no sense in higher dimensions, but the requirement was that L less or equal than 1, different from 0. I mean, I'm putting it as shaded as possible, because it really makes no sense in the k-dimensional case. I will illustrate now in the plot, given the time, exactly what are the motions, instead of being labeling everything and doing it slightly more boring. I think it's cleaner to look here in this plot. So along each, let's say, the x direction, I'm here sitting on the 3-2 sector. And along the x direction, I can just move a single elementary step forward. Then, of course, I can compose it and keep going along this direction. But at the elementary level, I have a single step that I can move forward. This is the k equals 1 case, or L equals 1, I'm sorry, in the notation that I'm using now, the L equals 1 forward step that we have already seen when we're discussing in the previous hour, the one-dimensional case. The same thing, so here it's in solid forward. The same thing along the y direction. So I have in dotted, I have the possible sort of elementary step forward. Now it goes up. And I could then compose it by taking multiple derivatives and keep going up. The same thing happens going backwards along the x direction. In solid, I have now several steps that I can make, right? So that I've highlighted here in blue. There's the single step, there's the double step, there's the 3-step. Of course, I can still iterate them. So I can iterate, in this case, I can only iterate the single step to twice or thrice, not more. And the same thing coming down here. But I just wanted the dotted, not the dash dot. So it's this one. There's a thing, and there's that dash, that dotted, that comes there. So those are the two possibilities. And then I have dash dots. Dash dots are just composition of solids and dots. So I mean, I can go dotted forward and solid back. So I have a couple more elementary things. So what you can see is that you can think of this as splitting the possibility of Stokes data, Stokes vectors, into quadrants. And there's basically nobody on the first quadrant. First quadrant is basically empty. The second quadrant is mostly empty. There's a few guys up here, but it's mostly empty. And the same thing happens for the fourth quadrant. It's mostly empty. There's a few guys here, but it's mostly empty. And the third quadrant is pretty full, generically, of course. And this you could, you can go from quartans to orthants and just define what happens in the k-dimensional case, and it's going to be quite similar to what I've just said. So this is how things organize. Of course, that then I have, do I have another plot? No, anyways, okay, so let's just stop sharing and let's go to let's do the iPad first, and then let's go to Mathematica with the final exercise that I will give to the students. Okay, so that's sort of the idea. Let me just, what I've said in words, let me just put here. So I have this possibility of a lattice of possible Stokes data, that they would be somewhere here on this integer lattice. And I'm going to be ultra schematic. So this guy is empty. This guy is mostly empty. Mostly empty. And this guy is pretty full. Generic. And so now imagine the k-dimensional generalization of this. And now let's find all these Stokes data. Well, not yet, not today, but next time in an example. I mean, then of course we go example by example, but I will tell you in an example. And we're trying to see if we can generalize this for arbitrary problems, at least in the KDBR. And you could say, okay, that looks interesting, but it's rather abstract. So can we make it any more precise? Well, rather than precise, can we illustrate it anyway? So here's the final exercise that I'm gonna give out to the students, which is to look at, and I'm sorry for the equation that I'm gonna write down, but it's really, this is the simplest example that produces all these features. So it's not, that doesn't mean that it's a simple example, but I'm sorry, I have to put my glasses, otherwise I cannot even read this example. So let's look at this equation. It's sort of a modified Riccati-like equation, which has singularities on the x and y axis of the Borel plane. Let me just write down the equation. If anyone finds a simpler example which illustrates all these things, I'll be glad to know, because this is not the simplest possible example to look at, but it was, it's nonetheless still pretty solvable. Okay, plot Borel singularities for this, so that's the exercise. Plot Borel singularities for this problem using Borel-Padé approximants that we've already discussed. This takes a little bit more of effort. So that's why I will make the notebook available today. Let's go to the notebook. If I know where the notebook is, it is here. Okay. So here's what's going. I'm not sure why Roberto called this exercise 89, but so here's there's the equation that we're trying to solve is written here, and he's sort of producing data for that equation. And then we go on and we start looking at Borel-Padé poles of here we're starting with the perturbative sector. And we can see in blue the Borel-Padé poles. So we can see singularities at all forward guys. So green singularity is sort of this elementary motion that I could have. And then, as I said, because I'm exponentiating alien derivatives, I can keep iterating these elementary steps, and I have the orange singularities and say, well, okay, those are all there. What about backwards? Then we do the 3,2 sector, and as you can see, the coding starts being a little bit more intense. But if you do that, then you can start seeing stuff appearing. And so again, now I'm sitting on the 3,2, and I see in green are the single step singularities. Of course, I mean, there's not a lot of data. I mean, I think you guys should improve a little bit. I think, Roberto didn't run this for a long time, and that's why we have not a lot of Borel-Padé poles, because it didn't generate so much data. But I mean, if you guys are interested in this exercise, you should let it run for a few more hours to get more data. And you see how Borel poles are all appearing already in the singularities which are expected. He did do a quicker case, which is the 1-1 sector, and he has more examples. So I'll make the notebook available, probably give it to Ricardo or something today, and then you can, because I think this is already a more technical exercise. You probably don't want to be wasting hours trying to code it, and you can get yourself a basis on how to code it to try to play a bit with it as well. The other exercises from the 2 past classes, you should try to code them a little bit. Let's just see the actual plot that we have in the lectures. If I'm not mistaken, is this one. So here we go. So here we have the perturbative, and you see that we have, so this run for a big more time. You can see these guys, and here for the 3,2 sector, you can clearly see all these guys and Borel-Padé singularities attached to many of these guys. So green, again, are the singularities that you expect to see straight off, and orange are the iterated singularities that you expect to see, which there was a plot maybe here. Yeah, so you see that I have this guy, then I can iterate this diagonal step to go to the 1,4. So I can go from 3,2 to 2,3 and then iterate it to 1,4, but I can't reach, for example, 2,4. There is no combination that takes me there. And so you see this here. Yeah, okay, we don't have enough precision. You see some poles there. There should be some Borel-Padé poles if we had run it a bit more, but there won't be any Borel poles over there. All right, so that's the idea. Let's see how long do we have. I still have 20 minutes or 10 minutes. Let's look anywhere. So let me see. Let me say 2 more things before we can move to examples. So maybe even I can start a word on examples today, but let's say 2 more things before that one. So let's go back to the iPad. Okay. Wait, turn on the iPad. Okay. So 2 more things I want to say. The first is basically, now it's 2 comments on this higher dimensional story. The first comment is, you could ask yourselves, what is the commutator of 2 alien derivatives? Whatever. Is this an alien derivative? Is there some sort of algebraic structure here? Well, it's more complicated than that, because this is open. It doesn't close, not necessarily. So the simplest way to do this, so this is, again, I'm not going to give all the details, but we introduce a slightly more generic, because this is going to give you an open algebraic structure. I need to introduce, well, we call it G. Not sure why we called it G, but anyways. Sort of a generalized quote-unquote alien derivative. It means nothing except from an algebraic point of view to do the calculation, which is of this form. And you could say, why did you introduce this G operator? Well, we just go back to the alien derivative, which was here. And you see that that looks almost, except that I'm not calling this guy a Stokes coefficient. Just take it for the moment, and now I'll just do the calculation, and you will see why I'm saying this. Because these G's, they have a quite simple algebraic structure. So if you just do the calculation, you can compute the following: Gn, I'm sorry, the first vector is V, on V commutator with Gm on U is going to give you Gn plus M. So this has some sort of Virasoro-like flavor. V dot M times U minus U dot N times V. Okay, this is a very simple exercise. What does this imply for alien derivatives? Let me just, so that it's consistent, that should be an N. Can I compute the delta N, delta M alien derivation commutator? Well, with this result, yes. Let me try to put, this is just, if you want, given by, so follow the white calculation, and the green calculation is going to solve for us the white calculation. This is just that. And if I do the calculation, so now I know I'm computing the commutator of L derivatives, so I'm just using that result, I find this result here. Now you see that the right-hand side is not necessarily, I should be putting arrows on everybody, is not necessarily an alien derivative. That's what I meant by that the structure, the algebraic structure is open. So the commutator of two alien derivatives is an alien derivative if the following happens. This guy, this combination of Stokes vectors. No, I'm sorry. S is proportional to Sn plus n. So at this stage, this is it's a funny comment to say, okay, that's a funny comment. Why would I care, for example, in the context of the things we've just been discussing? Well, because I can make a trivial calculation, which is just elementary orthogonal. So where was my trans series lattice? So I can make just elementary orthogonal direction. So I can just make the calculation of the blue lines. And if I do the calculation on the blue lines, I can compute this result. By E, of course, I mean the canonical vector on the direction, well, X and Y in the plane that I had, but generically anyone, any direction. And this is 0. And this is sort of, this is the trivial to check. And if you do that, you sort of understand why there's nobody there. Okay, they say, all right, that's kind of cute, but what about the yellow relation? Well, the yellow relation seems the curiosity. As we will see, it's a curiosity that actually materializes in example. To be honest, I don't really still understand exactly why. So that's the first comment I wanted to make. There's a second comment I want to make. If I can find it, yes, here it is. The second comment I want to make is the following. So let's go back to the generic trans series that we were discussing a little bit earlier. What was it? Multi-parameter trans series. And we said, okay, let's work in the example which everything is non-resonant. And so we had this discussion. Well, what happens if this is not verified? So that was my first comment. Here's my second comment. Let's put it with a title, resonance. This is actually quite important because this is verifying examples in a lot of examples, almost all examples. So you could say that what I've been telling you so far was just, warming up to what actually is happening. So we have the vector of instanton actions. And now, and we were asking before that things were non-resonant. Well, now we're going to say, what happens if they are resonant? Then, oh, let me not write it again. Let me just go back to what I had. Where was the non-resonant case? So what I wrote before was that there was no labeling of a multi-instanton sector that would kill the argument of the exponential. So I was going through all multi-instanton sectors, and this guy was always never collapsing, so either enhanced or suppressed, depending on the sign of instanton action, was always there. Well, what happens otherwise? Well, otherwise, so the system is going to be resonant if there is some vector, again, it's a different font in LaTeX, non-zero vector in the lattice such that n dot a is equal to 0. And we call this, well, that's just a name, an action correlation. So let's illustrate again. I'll illustrate maybe with plots. So this is going to be relevant when k equals 2, only the problems that we will discuss next time, where the instant actions. So for a moment, just accept that this is what's going to happen, and we'll discuss about this next time, are basically A and minus A. And you see, oh, well, with A and minus A, obviously, this is a resonant problem because there's this vector here is a direction of resonance. Okay. And let me, I think we have, yes, 10 minutes to go. Let me just show you some plots of how that goes about. Let's see. Here we go. So let's look at these plots. So what I'm plotting here in what's figure 30 is the perturbative sector. So I'm telling you, so here's the lattice of trans-series sectors. That's the perturbative sector, and these are the multi-instanton guys, 1, 0, and these are the multi-instanton guys, I'm sorry, n, 0, and these are the multi-instanton guys, 0, n, and I have a bunch of them. And in this case, I don't have resonance, so I have chosen instanton actions A1 and A2, which are rationally independent, both, real, symmetric, but rationally independent. And then I project, these dotted green lines are the projection upon the Borel plane. That's the blue line here. And that's where singularities sit on the Borel plane. And here I have the resonant case. And you say, well, there's no difference. I agree. At the perturbative level, there's not a lot of difference. Let's go back to the I-plane. However, at the non-perturbative level, things are more tricky. And there's some novelty. So why is not showing that? Here we go. Sorry, what's happening? Here it is. Okay. Now, there was a projection map, you may recall. So I'm illustrating all this in front of it. There was the projection map, which started at the lattice of possibilities and came down to the Borel plane in the way that we've discussed. And now the kernel is non-trivial. And the non-triviality of the kernel was not seen at the perturbative level. So you ask, where is this non-triviality of the kernel? Let's go back to the plot again. And I'm sorry, I'm not in person. It would be much easier jumping between Blackboard. So here, and we have the 3,2, the plot that we've already seen. And I'm sitting there at the 3,2. And this is my lattice of possible singularities. This is the non-resonant case. And I can move one step forward and then I can iterate, one step forward and I can iterate. And then I have different steps back that I can also iterate, which are these ones. So these are the possible singularities. And if I project them to the Borel plane, they're all there, living their own lives, independently of each other. But in the resonant case, you see that things align such that a lot of people fall on top of each other. And that's basically the fact that the kernel is no longer vanishing, or that if you want, the map is not one-to-one, the projection map is no longer one-to-one. And so we will need to deal with all these people sitting on top of each other. And we need to know how to deal with these guys. And so that's all I'm going to say about resonance, because this is really a feature very much associated with Polynomial V1, Polynomial V2, or and so that we will talk about it. So let's see, we have only 5 minutes. So I think I will end, unless Ricardo complains, I will end this lecture slightly early with 5 minutes to go. And then, all I have left to do now is applications. And I think that 5 minutes of applications is not worth it. And so to allow it in the last lecture, which hopefully eventually, I will just do a slides presentation so that I can make sure that I can cover as many applications as possible. So I think it should be okay, right? So we went on the blackboard with all the details of Resurgence, and now what I want to do now is string theory and matrix models. I'm not sure if I was maybe in bench theory. And then probably what I will do next time is I'll just do a slide presentation of basically of results. And that's probably the best idea. So let's say on the theory behind Resurgence and trans series, we will stop here. So if there's questions, go ahead.
Yeah, let us ask for questions. Any questions in the virtual room? Uh, 4:30. In the meanwhile, I remind that the next lecture will be on the 30th of May at 2:30 p.m. But please keep checking the website in case of problems of flight, something like that. Well, I don't know. Okay, I fear problems.
I'm planning to be there the whole Monday, the 30th. So,
the whole Monday, okay.
So, if in the morning people have questions about these 3 lectures, they just can find me wherever I will be. Isa.
Okay. So I think that people has no questions.
But again, I'll be there the whole day. So I mean, probably in the morning for questions, and then in the afternoon, I'll give, if it's okay, I'll give a slide presentation.
So okay, thank you very much, Ricardo, and let us stop now. So see you next lecture. See you.
Bye.
Bye.